At Atlas Pipe Piles, the manufacturing process begins with uncoiling hot-rolled steel coils that have been thoroughly tested for quality and strength. The coils are slit to the required width, flattened, and continuously fed into production without interruption, thanks to a spiral accumulator that ensures seamless material flow. In the forming stage, 5 rolling stations gradually shape the flat steel strip into a U-shaped profile, preparing it for welding. Precision rollers carefully align and burnish the strip edges to create the perfect conditions for a strong, clean weld. Next comes welding, where the edges are fused using electric resistance welding, ERW technology. Copper contact shoes pass a high electrical current through the strip, generating intense heat up to 2,700 degrees Fahrenheit to form a continuous, high-integrity, longitudinal weld. Excess weld material is removed for a smooth finish, and the welded pipe is ironed to achieve the final precise diameter, ready for testing and finishing. The integral ring, made from steel, titanium alloy, and magnetic yoke rings, represents an extraordinary engineering achievement. It includes the Guinness World Record for the largest integral ring, measuring 15.673 meters, crafted from austenitic stainless steel. This titanium alloy forged ring, known as ASTM 668, is designed with dimensions of 8,105 millimeters by 7,480 millimeters by 2,350 millimeters and weighs 160 tons. It demonstrates the advanced material science and precision forging technology used in creating massive structural components. The production process of the 4-megawatt power generator at Intergen begins with precision engineering of the generator's internal combustion engine. High-strength components are machined, assembled, and coupled to a heavy-duty alternator. A steel skid base is fabricated to support the entire structure. Once mounted, the engine and alternator are aligned with laser accuracy to ensure maximum efficiency. Auxiliary systems, including lubrication, cooling, and fuel supply, are integrated, followed by the installation of heat recovery modules for cogeneration. High-capacity exhaust systems are fitted to direct heat to absorption chillers or thermal exchangers. Electrical panels and control units are installed and tested to synchronize with the grid. Final steps include pressure and performance tests under load conditions. The completed 4 megawatts cogeneration unit is then transported for installation, ready to deliver simultaneous power and thermal energy with optimized fuel efficiency. Renk Zanini is a leading manufacturer of special gear reducers in Latin America. Headquartered in São Leopoldo, Brazil, with a state-of-the-art 13,000 square meters factory, the company produces high-precision gears using advanced German CNC technology and an ISO 9001 certified process. Renk Zanini offers a specialized product line that includes Toramax, planetary gearboxes for heavy-duty applications, Pentamax, high-performance parallel shaft gear reducers, and Fleximax, flexible gear solutions for various industries. The company also produces gear systems for the rubber and energy industries, supporting turbines, mills, and high-load equipment. State-of-the-art heat treatment, rigorous quality control, and 24/7 technical support, including upgrades and repairs, ensure exceptional reliability. Renk Zanini supports both the traditional and renewable energy industries with precision gear systems for turbines, generators, and hydroelectric plants. Critical components undergo advanced heat treatment processes to ensure exceptional durability, performance, and reliability. Continuous innovation and rigorous testing ensure that Renk Zanini products meet the highest standards. The SYT 2000 car body panel press, with 2,000 tons of capacity, is designed for the automotive industry. It features a moving bolster, quick die change, bolster up, and secure bolster lock for efficient manufacturing. The CNC lathe Morisaki NL 2500 showcases precision turning by machining a chess rook from a $2.50 inch 6061 T6 aluminum billet, presented by Glacier Machine Tools. Equipped with a 10-inch 3-jaw chuck and a $3.10 inch bore, the machine supports a maximum speed of 4,000 revolutions per minute. In this project, cutting speeds reached 450 SFM dry and 850 SFM wet, demonstrating exceptional machining flexibility. Featuring twin spindles, Y-axis milling, and live tooling, the NL 2500 efficiently combines turning, drilling, and milling operations in one setup. Its rigid construction, precise control, and advanced cooling management deliver smooth finishes, tight tolerances, and efficient cycle times for high-quality, intricate parts demanded by advanced industries. Kohler's cut-to-length line with special saw is designed for high-precision metal sheet processing. It delivers clean, accurate cuts on a wide range of materials. Integrated with advanced automation and a specialized saw system, the line ensures efficient throughput, minimal waste, and excellent surface protection, ideal for demanding industrial applications. The company applies advanced technologies in the production of weapons, missiles, and industrial explosives. They improve automated quality control processes and use rehabilitation technology for workers working in harsh conditions. The production process of nuts involves several key stages. First, steel wire or rods are cut into small blanks according to the required size. The blanks are heated in a furnace and then forged into the basic nut shape using cold or hot forming presses. After forming, internal threading is created through tapping or rolling. The nuts are then heat treated to improve hardness and mechanical strength. Surface treatments like cleaning and anti-corrosion coatings, e.g., zinc plating, are applied. Finally, each batch undergoes strict quality inspection before being packed and shipped to customers. This ensures consistent durability and performance in their final applications. Molten steel is poured into molds, solidified, heat-treated, and precision machined to produce high-strength railway wheels, axles, and industrial components at Lucchini RS. The foundry industry, vividly showcased in Powergus Fascination Gießen, is a dynamic fusion of ancient craft and modern innovation, offering creative minds vast opportunities to shape the future. Casting, the process of pouring molten metal into molds to create precise components, has evolved through advanced technologies and sustainable practices, spawning diverse, rewarding careers. Its history stretches back 400,000 years when humans tamed fire, but only around 6000 BC did they fire clay from molds. By 3000 BC, bronze casting produced masterpieces like the Mohenjo-Daro dancer, followed by an Alt-Mesopotamian prince's head 1,000 years later. Iron casting began around 500 BC, and 200 years ago, lightweight metals, titanium, magnesium, and aluminum, revolutionized the field. Today, Germany leads globally in casting technology, driven by rapid advancements in materials and methods, achieving world-class excellence. Casting is the backbone of modern industry. No sector, from automotive to maritime, functions without cast parts. As components grow more complex, foundry techniques must advance, supported by technical programs at German universities. The industry's allure persists, blending tradition with cutting-edge innovation. Careers in foundries are highly promising, even without degrees, through hands-on training in trades like foundry mechanics or model making, with pathways to become master craftsmen or technicians. The text introduces Marcus, a student who, after completing his foundational studies, tours a foundry, intrigued by casting as a potential career. The casting process, particularly hand-molded sand casting, is a meticulous journey from design to finished part, as detailed in the foundry's workflow. It begins with a customer's manufacturing drawing, which the foundry's design team transforms into a raw part drawing optimized for cost-effective production. For sand casting, a model, typically wooden, is crafted based on a model planning drawing. Modern foundries use computer-aided design CAD systems, replacing traditional drafting boards, to create precise, often three-dimensional designs. Constructors and model makers, requiring deep process knowledge and spatial visualization, account for material shrinkage, 0.6 to 1.2% depending on the alloy, to ensure the final part's accuracy. Simultaneous engineering (SE) accelerates production by enabling parallel workflows, meeting tight market demands. As castings grow intricate, molds and tools must match, demanding skilled constructors, often trained as model builders or tool makers before advancing through further education. Model making involves materials like wood, plastics, aluminum, or steel, often processed by computer-controlled machines. In sand casting, disposable molds are paired with models or cores, while permanent mold methods like die casting use reusable metal tools. The hand-molded sand casting process, vividly described, starts with a foundry mechanic placing a form box on a flat surface, positioning the lower model half and gating system. A powdery release agent is dusted over the model, followed by fine molding sand sieved and pressed to capture precise contours. Coarser backfill sand is layered and compacted with specialized tampers. Synthetic sand, replacing natural clay-bound sand, is standard in modern foundries for its consistency. Excess sand is scraped off, creating a smooth surface, and the mold is flipped. The second form box is aligned, and the upper model half, along with sprue and riser models, is set. The upper mold is formed similarly, with sprues and risers hand enlarged for easier metal flow. After molding, the form boxes are separated, and model halves are carefully removed, leaving a negative cavity. A sand core, crafted in the core shop to form internal features, is inserted with a ceramic filter to prevent slag inclusion. The foundry mechanic inspects the mold, then reassembles the boxes using guide pins for precision. The mold is now ready for pouring. A standardized aluminum alloy with 11% silicon, heated to 730 degrees Celsius, is poured into the mold. After cooling to around 300 degrees Celsius, the mold is broken apart, destroying the sand form. The sand core is shaken out, and the gating system and risers are cut off. In the finishing shop, residual burrs are removed, and the casting is blasted with stainless steel shot to clean its surface. The sand is reprocessed, and metal scraps are remelted, reflecting the industry's commitment to sustainability. This process, scalable to large castings like wind turbine hubs or ship engine blocks, underscores casting's versatility. Foundry mechanics, trained for 3.5 years, master both traditional skills and modern automated systems, contributing to high-tech applications in aerospace and automotive industries. The industry welcomes diverse talent, with women like a master model builder thriving in roles once male-dominated. Supported by the Verein Deutscher Gießereifachleute (VDG), foundries offer secure, well-paid jobs and lifelong learning. Marcus's tour, filled with sparks and precision, reveals a vibrant industry where creativity and technology cast the future. At Hydro Aluminum Recycling in Dagen, aluminum recycling follows a highly specialized process. Old window frames are first cut by shears and shredded. Magnetic and eddy current separators remove screws, plastics, rubber, and wood. A second shredder cuts aluminum into 4 to 6 centimeters chips without hammering, preserving material quality. The chips pass through a fine screening unit before reaching an X-ray transmission sorter. This machine detects and separates heavy metal alloys like copper or zinc using air jets. Pure 6060 aluminum alloy is collected and melted to produce billets with minimal primary aluminum added. The billets are then sent to extrusion plants to form new window frames, completing the recycling circle while saving vast amounts of energy and reducing carbon dioxide emissions. Automatic billet cutting by saw is a precise and efficient process used in metal manufacturing. Long billets are fed into an automated sawing machine, where a high-speed circular or band saw cuts them to predetermined lengths. The process ensures consistent sizing, minimal material waste, and high productivity. Modern automatic saws are equipped with CNC controls, cooling systems, and carbide-tipped blades to handle tough alloys. The billets are clamped securely during cutting to ensure clean edges and prevent deformation. After cutting, the billets undergo quality checks for dimensions and surface finish before proceeding to forging, extrusion, or further processing. The Hermel C60, a dynamic 5-axis mill-turn machine, is used for machining fan discs with pine tree groove cutters in 1.2738 steel. This advanced configuration offers precise, efficient processing for the energy industry, enabling high-quality results in complex geometries, such as fan disc components, with optimal performance and accuracy. The Hermel C60 features TNC 640 or S840 DSL control. It is equipped with a rotary table of 1200 mm diameter, offering a swivel range of plus or minus 130 degrees. Axis AC speeds are 15/400ths of a revolution per minute. Maximum load capacity is 1500 kg on the rotary table and 2500 kg on the milling table. At Ixamwada, hot forming of a 125 mm thick Hemi head begins with heating a steel plate to forging temperature, typically around 1200 degrees Celsius. The heated plate is then placed into a pre-shaped die. Through controlled hydraulic press forming, the material is gradually shaped into a hemispherical head under high pressure. Continuous temperature monitoring ensures the material remains ductile during deformation. After forming, the Hemi head undergoes heat treatment processes like quenching and tempering to achieve the required mechanical properties. Final stages include surface finishing, dimensional inspection, and non-destructive testing to guarantee structural integrity, making the Hemi head suitable for pressure vessels and critical applications. Oxy-fuel gas cutting of mild steel with an 850 mm thickness involves using a mixture of oxygen and fuel gas, like acetylene, to heat the metal to its ignition point. The oxygen stream then blows away the molten steel, creating a clean cut with precision, typically used for heavy-duty cutting operations. Steel forging transforms a solid iron block into a hoop through intense heating, hammering, and shaping. The metal is heated to high temperatures, forged into a ring shape, then tempered to enhance strength, durability, and structural integrity. The spring manufacturing process at the facility involves several key stages. Metal is supplied from Dnepropetrovsk in Zaporizhia, cut to precise diameters, and then undergoes drawing and heating in slot furnaces. The metal rods are drawn to specific lengths and sizes, with careful temperature control at every step. After heating, the rods are cooled, followed by tempering and hardening in a specialized furnace. The springs are then pressed to remove residual stress and checked for dimensional accuracy. The next stage involves shot blasting, which improves surface density and extends the spring's lifespan by removing scale and surface defects. The processed springs are then painted through an immersion method to protect them and enhance their durability. Each spring is carefully measured and classified based on height and diameter, ensuring that they meet the required specifications. The springs undergo final testing for hardness and mechanical properties to ensure optimal performance. Quality control is maintained throughout each stage of production, with strict adherence to industry standards. The finished products are then packed, with every spring being wrapped securely in stretch film for shipment. The facility uses advanced equipment for continuous monitoring of temperatures and mechanical properties to ensure top-quality products. With the ability to produce springs of various sizes, including custom diameters, the company meets the needs of industries such as transportation and manufacturing, supplying products that are reliable and meet the highest standards. Moenda is a machine used to crush or press materials, commonly used in agriculture and industry. In sugar production, the sugarcane crusher is used to extract juice. In other industries, it can refer to equipment that crushes or grinds various materials.